In Schoology, you will find a set of notes about VSEPR theory. You're always welcome to take your own notes as well. At the end of this set of notes, please date and topic, or please do summary and questions, and submit that. All right, so the shape of a molecule plays an important role in its reactivity. How molecules bump into each other, how frequently they can bump into each other in the right arrangements to make rates happen, makes a molecule more reactive or less reactive. What determines the shape of a molecule is always going to be the bonding and non-bonding electron pairs that we have. And so if we note those, we can easily predict the shape of a molecule. Is it linear? Is it bent? Is it trigonal planar? Is it trigonal pyramidal? Is it T-shaped? Note on pronunciation. Mr. Murray says this word trigonal. Mrs. Lee, for those of you who had her, says trigonal. Potato, potato. All right, so electron pairs, whether they are bonding or non-bonding, repel each other. So the pairs of electrons repel each other. What do I mean by pairs of electrons? Well, imagine that we've got a simple methane molecule. What they're talking about is this pair of electrons repels that pair of electrons, repels that pair of electrons, repels that pair of electrons. All right. So when that happens, those electron pairs are going to get as far away from each other as possible. And when that happens, you get an inherent shape of a molecule. You can get linear geometries, which have a bond angle of 180. You can get trigonal planar geometries, which have a bond angle of 120. You can get tetrahedral geometries, which have a bond angle of 109.5. And a couple others here, trigonal bipyramidal, where you have 90-degree angles on the top and 120 around the midsection, and also octahedral, where everything is 90 degrees to each other. Okay, so that's all. Some of these deal with expanded octets. Others of these deal with other exceptions or multiple bonds. So this idea that we just summarized is called the valence shell electron pair repulsion theory, or VSEPR. Right? So valence electrons are what we're talking about. Those are the ones involved in bonding. The electron pairs do what? They repel each other. Okay, so the best arrangement of a given number of electron domains is the one that minimizes the repulsions among them. Okay, so an electron domain is a bond or a pair of unshared electrons. So that would be a domain. That would be a domain. That would be a domain, or that would be a domain. Okay, so in terms of multiple bonds, it doesn't matter what kind of bond it is, a single, a double, or a triple. This is all one domain, just as this is as well. Okay, all right. So in your textbook, table 9.1 contains the electron domain geometries for 2 through 6 electron domains around a central atom. Also in Schoology, I have posted what I call the handy helper. The handy helper helps us get through these geometries quite quickly and figure out what we've got going on. So here is what the handy helper looks like. Okay, so when we talk about electronic domains, on the handy helper, they refer to that as steric number. So those things are the same thing. So again, if you want to write this out, you can just say domains, right? And that is just simply the number of directions bonding and non-bonding electrons go around the central atom. So again, as I think about it, if I go CH4 like that, how many domains do I have? I have 1, 2, 3, 4 domains. Okay. Likewise, if I did something like this, how many domains do I have now? We look to our central atom and we look around it. 1, 2, 3 domains around it. Okay, so again, that double bond there just counts as a single domain. I could also do something like ammonia. Okay, how many domains? Around that central atom, 1, 2, 3, and the bonding pair is 4. Okay, so that's going to all give you the number of domains. So that's what we go this way with. This one here, then we combine that domains with the number of lone pairs around the central atom. So this would have 0 lone pairs around the central atom. This likewise would have 0 pairs around the central atom. Yes, there are lone pairs out here, but those aren't around the central atom. Here we would have 1 lone pair around the central atom. Okay, so if we get that then, if we get our number of domains and we get our lone pairs, that gives us our overall shape. Okay, in general, it is important for you to know particular shapes. Certainly the ones in this first row are super important. Linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. A couple others that are important. Bent is always important. Seesaw and T-shaped are always important for us to know. So those are the ones that are probably the most important things for us to understand. But more so, you don't even necessarily need to know that if you can visualize this stuff in your head. But you need to get to a point where you can go ahead and you can identify what shape a molecule is from the electrons that are involved in it. I will be posting a Quizlet that has these different combinations so that you can start working on knowing those. All right, so having non-bonding pairs, there are a few ways that we can alter the standard bond angles for various geometries. So again, if I have a linear geometry, the standard angle is going to be 180. If I have a trigonal geometry, the standard angle is going to be 120. If I have a tetrahedral geometry, the standard angles are going to be 109.5. Okay, and again, as I said, sometimes you need to know the 90-degree angle ones as well that happen in trigonal bipyramidal or octahedral. Okay, but as long as you know that those are the standard, these standard bond angles are ones that you're going to need to understand. Okay, now if a molecule has a non-bonding pair, okay, those non-bonding pairs are physically larger than bonding pairs. They take up more space. All right, so as a result, their repulsions are greater and they tend to decrease the bond angles in a molecule. So here we have a standard tetrahedral, which has 109.5. If I move to ammonia, we've got a lone pair up here on the top. What is the effect of that? Well, it takes up more space, so it does more repelling down in this direction. So that means these angles up here on the top are going to be a little bit greater than 109.5, whereas the ones down here on the bottom are going to be a little bit less, and in this case it's 107. You would never need to know that exact number. You would just say a little less than 109.5. Okay, if we add even more lone pairs of electrons, like in water, again, this angle is going to get bigger. These angles are going to get bigger, but this angle between the O and H, that's going to get squished down to 104.5. Again, because these lone pairs are pushing down on the angle. So in addition to knowing that lone pairs will do that, the other thing that you should know is that double and triple bonds also do the same thing. They create greater electron density on one side of the central atom, and so therefore they are also going to do more repelling. Okay, so in a molecule like this, where our standard geometry would be trigonal planar, these angles closest to this double bond would get a little bit bigger than 120 degrees, and the angle down here between the chlorines would become a little less than 120 degrees. And that's indeed what we see when we measure those bond angles. When we get to larger organic molecules or larger molecules, it makes more sense to talk about the geometry about a particular atom than the geometry of a whole. So we would never ask you, what is the shape of this molecule? What we might ask you is, what is the molecular geometry around this carbon atom? In that particular case, you would go, oh, I've got 1 domain, 2 domains, 3 domains. Around that carbon atom, it would be trigonal planar. Or I could ask you around this carbon atom, and you would say, oh, I've got 1, 2, 3, 4 domains. Oh, around that carbon atom, it's tetrahedral.